This is the last section in this chapter, and we're going to spend 2 days on it. But it's on improper integrals, and so far we've learned definite integrals and indefinite integrals. Definite integrals are when you integrate and have limits of integration. Indefinite integrals are where you don't have those limits of integration. All right, well, the definition of a definite integral requires that the interval between a and b be finite. That means that the numbers a and the numbers b have to be finite numbers. They can't be infinity. It also requires that the function is continuous between a and b. And so far, I've only given you integrals between a and b that are continuous. If there was an asymptote or a hole or something like that, it has not happened between that interval. All right, so integrals that do not satisfy these requirements are called improper integrals. In an improper integral, either one or both of the limits of integration are infinite, or f has one or more infinite discontinuities or vertical asymptotes somewhere between the interval of integration. So for example, on a, these two are considered improper integrals because one or both of the limits of integration are infinity. The ones on b are a little bit harder to recognize. At first glance, you think, oh, there's nothing wrong with that. However, on this first one right here, where do you have a vertical asymptote on this function? At x equal 1. And that borders up to one of your limits of integration. So you're basically trying to integrate from a vertical asymptote that the graph never actually touches, and then on to number 5. The next one, you have a vertical asymptote at what? -1, right. And that happens to be smack dab in the, well, not smack dab in the middle, but in the middle of those limits of integration. So you're trying to integrate over a vertical asymptote. So those are the two things that make an integral improper, either having infinity as a limit of integration or negative infinity, or trying to integrate either starting with or having a vertical asymptote in the middle. But there's a way to deal with it, of course, and that's what we are going to learn. So we are going to consider the integral from 1 to b of 1 over x squared dx. Well, b is some unknown value. Well, b might be somewhere between 3 and 4. So graphically, if I were to integrate between 1 and some unknown number b, which I just randomly picked to be between 3 and 4, then graphically, what does that integral represent? Right, the area underneath that curve. Okay, so what I would do is, and if I wanted to continue to do this just in terms of b, then I would integrate from 1 to b, and it would be easier to rewrite this as x to the -2 dx. All right, what's the integral of x to the -2? Negative x to the -1, and then I would go from 1 to b. And if I plugged in my b, I would get negative b to the -1 minus plug in my 1. So I get minus a -1. So -1 over b plus 1. So I could identify b to be any number and find that area under the curve between 1 and b. All right, so we're going to use this concept to integrate from 1 to infinity of 1 over x squared dx. Now technically what that means is I'm finding the area under the curve from 1 all the way to infinity, which is kind of a strange thought because we're trying to find an area that basically goes on infinitely. Do you think that's possible? Okay, it is possible, and we're going to use the concept of limits. Think back to way back in Algebra 2 where you learned the bouncing ball problem where like a ball bounces half of its height each time that it bounces. What's the total vertical distance that it travels? And in theory, that ball will continue to bounce forever and ever and ever and ever. To the naked eye, it's going to look like it comes to a rest, but you can always, like, it'll always bounce half of its original height. We were actually able to find the total vertical distance that ball traveled. So we are, on some graphs, going to be able to find an area of kind of an unbounded region. All right, so what we're going to do is we're going to take the limit as b approaches infinity and integrate from 1 to b 1 over x squared dx. Well, I just did that up here. So the whole integral from 1 to b of 1 over x squared equals negative 1 over b plus 1. And if I take the limit as b approaches infinity, because it's an improper integral, the fundamental theorem of calculus does not work, because up at the top of your notes, the fundamental theorem of calculus requires that a and b be finite. So you can't just integrate and then plug in the infinity minus plug in the 1. So we're going to think of it in terms of a limit and think of, instead of integrating from 1 to infinity, we're going to take the limit as b approaches infinity and integrate from 1 to b. It's just the technique around dealing with an improper integral. And that's what you'll do all the time. All right, so what would this limit be? 1. Okay? So that area that extends forever, or that region that extends forever and ever and ever, actually has an area of 1. All right, so the definition of an improper integral and the way that you deal with it is that if you're integrating from some constant to infinity, then you're going to take the limit as b approaches infinity and integrate from that constant to b. Sometimes you'll have a negative infinity as your lower limit. So instead of integrating from negative infinity to some constant, then we can take the limit as, say, a approaches negative infinity and integrate from a to that constant. We usually let a, if we're replacing the number on the bottom, we usually let that be a. If we're replacing the number on top, we usually let that be b. But you can use any variable that you want. All right, sometimes we'll even integrate from negative infinity to infinity. And the way that you deal with an improper integral is you can really only deal with one type of improperness at a time. So if you're going from negative infinity to infinity, you need to integrate from negative infinity to some number and then plus that same number to infinity. We'll do one like that in just a second. The improper integral is said to converge if that limit exists, and that's your answer. Sometimes the limit will actually not exist, and therefore the integral diverges, and that just means that you can't, it's impossible to find that area since it's an infinite region. But you'll see all of this in the examples. Okay, so the integral from 1 to infinity of 1 over x dx. As soon as I see that infinity right there, I know that I'm going to have to use a limit. So I'm going to say, well, this is the same thing as the limit as b approaches infinity, and I'm going to integrate from 1 to b of 1 over x dx. And notation is a really big part of this, so pretty much anything that I'm writing up here, I would expect you to write on quizzes and tests. And the limit is the very last thing that we're going to take. So what is the integral of 1 over x? Natural log of x, okay. So since the limit is the last thing that I'm going to do, unfortunately I have to keep rewriting limit as b approaches infinity. Okay. Okay, so now we're going to plug in our b minus plug in our 1. And now I can go ahead and take that limit. As b approaches infinity, what does the natural log of b approach? Okay, I'm hearing 0 and I'm hearing infinity. Let's think about the graph of ln x. Yeah, so as x approaches infinity, the ln x is also going to approach infinity. And the natural log of 1 is 0. So because that limit equals infinity, technically that limit does not exist. So this integral is considered to diverge. Right. So it's kind of curious that we could find the area of the region bounded by 1 over x squared, but we can't find the area of the region that's bounded by 1 over x. And when we get to chapter 9, that will kind of explain it a little better. Okay, so in number 3, the first thing I see is that infinity right up here. So I have to say, well, this is the same thing as the limit as b approaches infinity, integral from 0 to b, e to the negative x dx. Okay, what's the integral of e to the negative x? Negative e to the negative x. So negative e to the negative x, from 0 to b. Plug in your b minus plug in your 1. So negative e to the negative b. I'm sorry, plug in your b minus plug in your 0. Minus negative e to the 0. Which, right, is 1. Okay, when I'm taking limits, negative exponents don't really work in my brain. So negative e to the negative b is the same thing as negative 1 over e to the b. And then plus e to the 0 is plus 1. Now, when I take the limit as b approaches infinity, I'm going to get 0 plus 1 or 1, right? Yes, so it converges, and the area on that last problem is 1. If you were to draw the graph of e to the negative x and bound it from x equals 0 to x equal infinity, then that area would be exactly 1. No. If you get, that's a good question. You don't have to say that it converges. If you get an actual number answer, then that is the value of the limit, and that's what, or the value of the integral, and that's what we're looking for. Okay, this one's just a little bit different. This time, we're going to take the limit as, okay, you want to use a approaches negative infinity. And then we will integrate between a and 0, 1 over x squared plus 1. And you don't have to use a. You know, I would say you could use b all of the time, except if we're going to integrate from negative infinity to positive infinity, then we're going to need an a. We're going to need 2 different variables. So it might be a good habit to get into to use a for negative infinity and b for positive infinity. All right, how the heck do you integrate 1 over x squared plus 1? Oh, y'all are so good. All right, so 1 over x squared plus 1, that integral is arctan x from a to 0. Notice that I am taking the time every single time to write the limit as a approaches negative infinity. All right, what is the arctan of 0? What angle has a tangent of 0? 0. And what would the limit of the arctan of a be as a approaches negative infinity? Okay, what we're going to have to do is we're going to have to visualize the graph of arctan. This is actually pi over 2 and negative pi over 2. Okay, so the limit as x approaches negative infinity of arctan x is negative pi over 2, so I have minus a negative pi over 2 or pi over 2. What you really need to know is you're going to have to be able to either visualize that arctan graph in your head or be able to draw it on quizzes and tests that you can refer to it. Because I'm going to ask you more than once to find the limit as arctan either approaches infinity or negative infinity. Yeah, arctan is the only arc graph that you need to know.